Now, our last conic section is a hyperbola. A hyperbola is the set of all points x, y in a plane, the difference of whose distances from two distinct fixed points called the foci is a positive constant. The graph of a hyperbola has two disconnected parts called the branches. The line through the two foci intersects the hyperbola at 2 points called vertices. The line segment connecting the vertices is the transverse axis, and the midpoint of that axis is the center. The hyperbola has another interesting axis called the conjugate axis. It never touches the hyperbola. Hyperbola also has asymptotes. Remember what asymptotes are. Here's an example that we've drawn of a hyperbola. Notice those asymptotes, they're the yellow lines. The hyperbola approaches those asymptotes but never intersects them. We have a conjugate axis here, we have the center at 0, 0, and we have the transverse axis. Now, if we have the hyperbola as a general second degree equation, then b must equal 0, a and c must have different signs. One can be positive, one negative. They can be equal, but one has to be positive and one has to be negative. There's one very common hyperbola, though, that has b equal to 1, and that is xy equals 1. Notice the asymptotes are the x and the y axis. The transverse axis is on the line y equals x, the conjugate on the line y equals minus x, and the center is at 0, 0. Now, let's look at hyperbolas that we're more interested in. Notice we have x squared hyperbolas and y squared. How do we tell? By the positive term. If x squared is positive, notice the hyperbola opens to the right and left. If y squared is positive, then the hyperbola opens up and down. The next thing we want to look at is the standard equation of the hyperbola. Notice that the only difference between this and the ellipse is the negative sign between the terms. We subtract rather than add for the standard equation of the hyperbola. So we'll do much the same work as we did with the ellipse. We also have hyperbolas where the center is at 0, 0. Did you notice that the center of hyperbola is not inside the hyperbola? It's halfway between the two branches. Let's look at the definition of the asymptotes of a hyperbola. Well, if we have a horizontal transverse axis, then y is equal to k plus or minus b over a times x minus h. Hey, don't try to memorize those. I'm going to show you an easier way to get those asymptotes. You don't want to memorize that formula. We don't want to memorize anything more than we have to. All right, let's do some examples. First hyperbola. Notice this is going to be an x squared hyperbola. In other words, it is going to open to the right and to the left. The center is at 0, 0. A equals 3, 2a equals 6, and that would be the length of the transverse axis. Let's find the asymptotes. Now remember I told you, we don't try to memorize them. We take x squared over 9 minus y squared over 4, set it equal to 0, and solve for y. You know how to do that. You could even put it in your calculator and make it solve for y. In this case, y is going to equal plus or minus 2/3 x. We have a x squared hyperbola, and so on the next screen that you're going to see, I'm going to attempt to sketch this hyperbola. Now please remember, it's going to be very rough because I don't draw very well. I got a pretty good x and y axis there. Not bad. So what I'm going to do is I'm going to mark off the transverse axis and the conjugate axis. And then I'm going to attempt to draw a rectangle connecting those points. Then we'll draw the diagonals of that rectangle, and guess what? Those are the asymptotes. And then we just fit that hyperbola right in there as smooth as you want. Okay, let's try another hyperbola. y minus 2 squared over 4 minus x plus 3 squared over 9 equals 1. Notice a hyperbola always has to equal 1, just like an ellipse did. The center there is at minus 3, 2. Remember, the center is always xy, no matter how this is written. The length of the transverse axis is 4. B equals 3, 2b equals 6, and so the length of the conjugate axis is going to be the 6 there. Now, let's get some asymptotes. Remember, we take that hyperbola, we set it equal to 0, then we solve for y. Now be very careful, this is a little bit more difficult than the previous one. Let's multiply both sides by 4, and then let's basically take the square root of both sides. Y minus 2 will equal plus or minus 2/3 of x plus 3. Those are our asymptotes. All right, let's take a hyperbola that's in standard form here and fix it up. Notice the first thing we do is subtract the 36. We got to make it equal 1, so we're dividing by 36. Notice what's coming up. Hey, that thing started out looking like it might be an x squared hyperbola, but since I had to divide by negative 36, it reversed the signs, and so really I got a y squared hyperbola, made it a y squared hyperbola. Okay, let's try a hard one. 9x squared minus 4y squared minus 18x plus 16y minus 36 equals 0. All right, just like we did for an ellipse, group the things, but we've got a sign that we have to watch out for here. The 9x squared and so forth, that's easy. 36 plus 9 on the right. Good. Now notice we had to factor out a minus 4, so it made it y squared minus 4y. If you don't get that right, it's going to impact the center. So we get 9 times x minus 1 squared minus 4 times y minus 2 squared equals 29. Oh, what a horrible number this is. We'll start by dividing everything by 29 so that we get it equal to 1 on the right-hand side. Okay, but you know what? We're still not done. We have to go through and divide the first one, numerator and denominator, by 9. The second one, numerator and denominator, by 4 equals 1. Woo! This is ugly. Hooray! Hooray for computers. Let's see if we can get a computer to tell us what this thing looks like instead of what we've got there. And you know I'm going to get you a pretty picture from a computer. Remember that last example? I said the equation was ugly. Well, hooray for graphing software. Look at that. That's a right pretty hyperbola that we have there. And we've got the asymptotes, and we have the hyperbola showing. We're in good shape.